Okay, let me get started. This is Shiga box. I go to the annual meeting with Simons Foundation every year, and every year they give me some souvenir. And one year they gave me this cigar box, which actually contains my chalk. I guess that this is a reference to the fact that Jim Simon used to smoke cigar, and it has actually on it says prove it. So today I guess I will prove the modular invariance of toroidal compactification. So that's what I do. So toroidal compactification. So what we consider is a map from two-dimensional worldsheet to torus in d dimension times r of 1 time and 25 minus d dimensional flat space. So I take the bosonic string has to be on 25 dimensions. So I take d dimension out of 25 dimension Minkowski space and compactify it on torus. So there are two different ways of parameterizing torus. So one is to use coordinate xi, which is periodic. Where mi are integer, so there are d of them to raise to the power of d. Okay, so or I can say that between d, z, and I goes from 1 to d. So this is a square, or in general, some high dimensional square where you periodically identify size with periodicity to pi. Okay, and then we say that we have a metric on this space, which is of this form. Okay, so if you have a map from worldsheet to torus for this part, so for now we'll pay attention to this part. At the end, we're going to combine that with Minkowski space and construct string theory and discuss spectra, etc. But for now, let's just pay attention to the part of the map from this to this part. So then the action on the worldsheet will be of the form of the standard notation is 1 over 4 pi, and two-dimensional metric, I think I keep to be conformally flat, and then the action like that. Okay, so the metric is symmetric, and positive then. I choose the normalization to be 4 pi so that the 2-point function takes the form of log of z minus w square with coefficient 1. If you choose 1 over half, then there will be 2 pi over here. So it's just a choice of the notation, the convenient normalization, because we don't get 2 pi for the probability. Okay, we could add what's called a B field, which takes this form. Okay, where B field now is unsymmetric. The metric is symmetric. Oh, so these are bars. I'm sorry. So this is z derivative with respect to z. This is derivative with respect to z bar, and the metric is symmetric. So if you consider bilinear of these, then you can consider either symmetric or unsymmetric part. In general, you can have d by d dimensional matrix multiplying to this, so I just decompose that to the symmetric part and the unsymmetric part. And this reflects the fact that when we discuss the spectrum of the massless spectrum of 3 in the case of 26-dimensional Minkowski space, it contains metric and unsymmetric form and the Dirac. So this corresponds to different. So if you have unsymmetric tensor in this 26 dimension, you have 3 types of field. You have unsymmetric tensor with both components in this side, or both components in this side, or mixed one. So here I'm considering the one where all the components are on this side, because I'm ignoring excitation in this direction. So we'll later, after we thoroughly understand the spectrum, the part of this conformality theory of the worldsheet, which corresponds to the map of the worldsheet to the torus part, then we'll discuss other part. But let me for now discuss this part. So then we'll just come. Okay. So including this is slightly more interesting, but it doesn't change the main point I would like to make. So for the purpose of the discussion today, I will just only consider the action with metric. Once we understand how to do this, it's very straightforward to include the B field part. So we just consider this sigma. Okay, so you can think of this as just a standard torus with a metric, flat metric given by this. I forgot to say that Gij is constant d by d symmetric matrix. So this is the one presentation of torus, namely that we have this periodic square torus, is orthogonal. And I just wrote 2-dimensional part because I don't have higher dimensional blackboard. So if I had d-dimensional blackboard, I would draw a d-dimensional space. So in this presentation, the d-dimensional torus, which I often denote T of d, is defined to be d-dimensional flat Minkowski space divided by this equivalence class, and that equivalence class is xi. Is equivalent to xi plus 2 pi n. Okay, which is an integer. Okay, so that's one way of presenting this torus. But there's another way of presenting this torus, which is the following thing. So since Gij is a symmetric real tensor, so we can of course diagonalize it. We can diagonalize it and with some eigenvalue. And because of that, we can always write Gij into EIA, EJB delta AB. So what I do is first diagonalize Gij, but then also rescale the. So we can diagonalize Gij. First you can diagonalize Gij by some matrix. So you can do this by some matrix UIA, UJB, and then lambda A of delta AB. So you can always do that, right? So because here I'm just diagonalizing the d by d symmetric matrix by some orthogonal rotation by U. So A and B and D and both A, B, and Ij go from 1 to D. And then what I do is just rescale UIA by square root of A and define this to be EIA. So if I do that, I can absorb this eigenvalue into the normalization of E, so I can write it into that. So by appropriate basis, you can just have a standard normalization of flat Euclidean method. Okay? In the Lorentzian signature spacetime, these are called local Lorentz in general relativity. So you can see that you can represent the Riemannian manifold either in terms of the metric or in terms of local Euclidean frame. So this is the equivalent description of Euclidean Riemannian manifold. So this is a convenient presentation for the following reasons. That if you do that, then we can also choose to describe this dynamical variable x in terms of this basis. And so that I define xa to be equal to EIA of xi. Okay? So the nice thing about that is that if you do that, then the action expressed in terms of a variable is just diagonalized with no additional concept associated with it. And except that now the periodicity is more complicated. Because periodicity now goes like that. Okay. So we just use same kinetic term as if you were in the original Minkowski space, except that you periodically identify the space into this. Okay. So therefore, now the presentation of torus is slightly different because previously we had this torus. So maybe I should use this as P0 to distinguish from what I'm going to do. But then I can define new torus, which is periodically identified in this way. Okay, so this gives rise to some more generalized notion of lattice in d-dimensional Minkowski space. In the last lecture, remember that we considered two-dimensional plane. That was a discussion not in target space, but on the worldsheet. But in the previous lecture, I considered, and in fact, I remember my presentation was not very clear, and I apologize that I was confused by something. But there I chose two vectors, and then because we consider a lattice generated by these vectors, integer generated by a linear combination of e's with integer coefficient, and we consider these lattice points, right? And then we periodically identify the two-dimensional plane by this lattice translation. And that gave rise to two-dimensional worldsheet torus. We do the same thing for higher dimensions. So in higher dimensions, imagine we are in d-dimensional Euclidean space, and we consider translation by this. So you can imagine that the lattice in d-dimensional space. And so basically what the new way of presenting torus is consider this d-dimensional Euclidean space divided by the equivalence plus by the lattice, where this lattice is basically the collection of discrete points generated by this lattice vector. Okay, you can think of this as generalization of these lattice points. Okay, I hope this is clear. So what this means is that you consider this d-dimensional Euclidean space modulo this, but on this space we can just use this action. And this actually is more convenient for many purposes. So instead of talking about the matrix, we can just talk about the lattice. So when we consider string theory on torus, the target space is torus, we consider lattices. Lattices are nice because we have a variety of classification of lattices, and there are lots of interesting mathematics associated with it. For example, just a few years ago, Fields medals were awarded for classifying lattices in 8 dimensions and 26 dimensions, which allows the densest sphere pattern. So if you have, so there's a question of how to pack spheres in various dimensions. I guess in 3 dimensions, this was a question actually even considered by people like Johannes Kepler. So it's called Kepler problem. And so this turned out to be a surprisingly difficult and deep problems. And but finding that way to pack sphere is actually the same as finding suitable set of lattice with certain properties, like difference between the shortest difference distance between neighboring points is determined by unit length or something like that. So this was actually studied, and in 26 and 8 dimensions, this was the complete classification. And the person who, a mathematician who discovered that, she got the Fields Medal. And so this was the important discovery. Actually, the hard solution in 26 dimension is very closely related to what we're going to be discussing in heterotic string construction. So this is very interesting. There's actually a very nice article on Quanta magazine recently about some new result in other dimensions. There was a question of whether her approach is usable in other dimensions. And there was some new result evidently that people discovered that doesn't work in certain low dimensions. So these are, so the description of torus in terms of lattice is very useful because there are a lot of things known about lattices. So that's very convenient. Okay, so I spilled water on the table, so my notes are wet, but it's okay. So what should I do? Well, first we should. So what we need to do is to first of all solve the equation of motion, and then find suitable way to quantize the space of solutions. And so we need to solve. So we need to find solutions to this equation, modulo this identification. The only difference is that we have this identification, modulo lattice translation. Okay. So there are two things happen if you consider a string on torus. One is that X is not periodic anymore. So that means that, for example, if the worldsheet is cylindrical, if the worldsheet is cylindrical, which means that XA is a function of sigma 0 and sigma 1, and if sigma 1 is periodic, when X goes around the worldsheet cycle and come back to the same point, the value of X does not have to be identically equal to the original one. It could be different modulo translation by lattice. So that means that the condition for the periodicity is that XA sigma 0, sigma 1 plus 2 pi does not have to be XA of sigma 0, sigma 1, but can differ by some translation in the lattice direction, right? So, so that means that you can differ by some omega A, where omega A is in the lattice, on the lattice. So you can periodically identify X modulo lattice. So that means that X stereophix does not have to be a periodic function. It only has to be periodic modulo translation. So this is called winding number. For obvious reason, namely that when you consider this two-dimensional worldsheet as a cylinder mapped to torus, question is how many times the torus wraps the target space in which cycle of the target torus. So this is called winding. X can also have momentum. That is, so this you can think of this as a zero mode in sigma 1 direction, but there's also zero mode in x0 direction. So so this is a winding number. So there is this winding number. Okay, so that's one new feature of string on torus. Another new feature is that momentum is quantized. This is also not very surprising. This is something we are familiar with even in the particle theory, not in string theory. Because imagine that, for example, you have a particle living on the circle. Then we learn in quantum mechanics that the wave function of that wave function of the particle momentum has to be quantized, because the wave function has to be periodic as a function of the torus. So that means that so suppose you have a wave function which is a function of x. Okay, so the wave function is a more Fourier transformation of this, right? So we can ask what is the Fourier mode. But if x is a periodic function, then you have to have periodicity. So this leads to momentum quantization because Fourier mode becomes discretized, right? So it's the same thing for here. So what it means is the following. So suppose you have a Fourier mode like e to the I k x, where x is I k a x a, where x a is a zero mode of x. Remember that when we find the solution to this equation. Okay, so maybe I should remind you that what are the solutions to this equation? Okay, so let's start from this. So what are the solutions to this equation motion? Well, so we have this coordinate sigma 0, sigma 1, and sigma 1 is periodic. So that means that XA has to be periodic modulo this. So that means that so what we can do if you have a situation like that is first take care of this part. So I can write XA sigma 0, sigma 1 to the x0 of A. So it's kind of hard to distinguish 0 and A, and especially with my handwriting, but let me try my best. So x0 of A of sigma 0, sigma 1 plus WA, omega A, and sigma 1. So suppose I write it this way. Over 2 pi. So if I write it in this way, then this part is taken care of because if sigma is shifted by 2 pi, this gives rise to that. So that means that this has to be periodic. So that means that the sigma 0 A, sigma 0, sigma 1 has to be periodic, so you can have something and expanded in power of I and sigma 1 with integer summation, right? So you can do this Fourier transformation. This will be a complete solution. Well, the complete basis, but then what you need to do is what you need to do is to add x. So these coefficients can be x0 dependent. So we should add this possibility. So what you find then is that well, so the worldsheet metric is minus d sigma 0 plus square plus d sigma 1 square. So let's take this to be Lorentzian signature. So then you can write this as minus of d sigma 0 plus d sigma 1, d sigma 0 minus d sigma 1. So you can write z to be sigma 0 minus sigma 1 and z bar to be sigma 0 plus sigma 1. And so if you do that, then with this equation of motion, so we have del bar of x. So we can write x to be a sum of function of z and another function of z bar. Okay, so that means that this can be become linear combination of sigma 0 plus sigma 1 plus another one of e to the I and sigma 0 minus sigma 1. So that's one term. But there is another possibility. Because we can also have, so this is the solution. And another solution can be of this form. Okay, another solution can be of this form. T0, TA, the momentum. Because del bar of this also vanishes. So we allow this possibility. And the wave function associated. So you can think of this as the sorry. So that means that the total solution so after doing this, we can write the total solution to be equal to the center of mass plus twice of PA sigma 0 plus WA sigma 1. So this is momentum. And this is winding number. And then you have excitation. Where I chose the notation sigma plus minus plus minus sigma 0 plus sigma 1. So this is the expansion. The difference from the flat space case we discussed is that we now have winding number part, and then we are going to see that momentum is quantized. So to see the quantization of momentum, we do the following thing. So the wave function of this state with this momentum p would be to have a wave function of this type, where xa is a zero mode coordinate, the center of mass coordinate. But this has to be periodic. So that means that it has to be invariant under 2 pi EAI MI, where M is in Z. So therefore, this thing is in the lattice lambda. Okay. So however, you want the wave function to be periodic. So that means that e to the I TA EAI MI has to be equal to 1. Okay. This is possible. This is there is a 2 pi. And this is possible. This is possible if and only if P times E is integer. Namely, that this is possible. But this is possible only if PA EAI is an integer. So the correction of PA, so that PA EAI is an integer, is called dual lattice. dual to the original lattice number. So where the original lattice was this one. This was called lattice. This was called lattice. This is the definition of original lattice. And then this is the definition of its dual. Okay, the lattice generated by lambda of E is d-dimensional, but dual lattice is also d-dimensional. It spans d-dimensional space. So, for example, let's take an example of two-dimensional lattice we consider x and y. So, suppose you have two vectors E1 and E2, and suppose you consider lattice generated by these vectors, then what is a dual lattice? Well, dual lattice is so that it's also normal to the original lattice. It's also normal to the original lattice. So what does it mean? So first of all, so if you have E1, so if you have EI star, so suppose this is, so let's call this. So let's consider generator of dual lattice. So let's see what the generator of the dual lattice. So there must be, so you should always be able to write this to be linear combination of EA, I, NI, where NI is an integer, right? So then you can ask, well, what kind of property that this dual basis should satisfy? Well, the obvious condition is that the EA, I star, EA, J is delta ij, right? And so that you can choose that as a condition. So that means that, for example, that means that if we have this, then E1 star should be orthogonal to E2. So you have to have orthogonal to E2, but should have a unit inner product with EI. So that means that I guess it should go into this direction. So this is E1 star. And E2 star should be also orthogonal to E1. And so it should go in this direction, I guess. So this would be E1, E2. So I wish I had a color chalk actually. So this was the original lattice. And then this is a dual lattice. Right? So that's sort of a relation between the original lattice and dual lattice. It might be easier to consider one dimension. So for example, T1 is circle. Right? T1 is circle, and you can consider a circle of radius r. So what is the circle of radius r? Well, circle of radius r has circumference 2 pi. So you can consider a real line and periodically identify a real line by period of 2 pi r. Right? And this can be regarded, this translation by 2 pi r can be regarded also as a lattice translation. So this is a very simplified version of the lattice where you periodically identify real point of real line by translation by 2 pi r. So these are lattice points in 2 dimensions, 1 dimension. Okay, so this is a lattice. This is a lattice. Okay, so what is a dual lattice? Dual lattice has to have the normalizable inner product. So that means that the dual lattice should be on the same radius. You should have the radius 1 over 2 pi. Okay, so that would be a dual lattice. So that the product of this and this gives you integer. Okay, so So this is a space where winding number is, because if the string goes around once or twice, wind around integer multiple of 2 pi r. So therefore, this is a space where winding number is. This is a space where momentum is. Okay. So these are dual features. Okay. Now, if you look at, so what we are going to see is a very interesting structure in the spectrum and operator algebra of this two-dimensional theory, which correspond to the spectrum of particle and the interaction of string in space-time. That is that the whole framework of this string theory is invariant under exchange of winding number and momentum. So that means that, string theory compactified on the torus characterized by the lattice, lambda, is actually identical in any possible way to string theory compactified on the dual lattice. And so that's what we'll see in the next half an hour or so. And this is actually the first instance of phenomena in string theory called duality. That there are two seemingly inequivalent descriptions of identical physical phenomena. And so we'll see so this is originates from the term dual over here. That the string defined on torus with characterized by lattice is the same as string theory defined on the dual torus characterized by dual lattice. Okay, so let's see how this works. Okay, so we have seen that this string coordinate sigma 0, sigma 1 has a parameterization xa minus I dA z plus z bar plus half of I omega A z minus z bar plus summation n non-zero of 1 over n alpha n e to the minus nz plus alpha n bar a e to the minus n z bar. Okay. So this is the expansion. So initially I had this coordinate sigma 0, sigma 1, but then I rotated so that that is equal to sigma 0 plus sigma 1, and z bar is minus sigma 0 plus sigma 1. I think this is the notation. So sigma 0 is like I tau, or tau is a worship ingredient. Okay, and the important thing is that the P A belongs to dual lattice, and omega belongs to the lattice, which we use to define the d-dimensional torus. Okay, so this is the entire characterization of string on torus. There is no metric, you don't have to write metric or anything. The action is 1 over 4 pi, the integral of del x del bar a with a flat unit normalized vector. Okay, so this can be decomposed into left moving mode, which depends on x, z, and the right moving mode, which depends on Z bar. Where, for example, the left moving mode is equal to x left A minus I P left A Z plus excitation. And then right moving mode is the zero mode for the right moving part. And right moving momentum and like that. Where important thing is that left moving momentum is a linear combination of the original momentum plus 1/2 of winding number, and right moving momentum is the difference of the momentum and winding number. So you can think of this as sort of living in the linear combination of lattice and dual lattice. But this is a natural decomposition of XL to be a linear combination of this holomorphic one and anti-holomorphic one, which as it should be if this is a solution to del del bar of x is equal to 0. If you have a solution to del del bar of x equal to 0, one should be able to decompose the solution to the left moving part and right moving part. So once we have that, we can decompose that into this form. Okay, so then we can write down the Virasoro generators associated to it. So the left moving Virasoro generator is given by this, just like before. And the right moving Virasoro generator is written like that. Except that the alpha 0A is now P left momentum and alpha 0 bar A is P right. So when the target space is flat, Minkowski space or Euclidean space, the P left for zero mode part of alpha oscillators are identical. But now they are different because they are different by the sign in front of the winding. So if we have winding numbers, there is a difference. But there is actually a very peculiar thing, which is that so if we look at this action and also the product between vertex operators, namely that the operator which carries momentum, there's actually a peculiar symmetry, which is to change the sign of P left. So so it turns out that the spectrum, the representation of the Virasoro algebra and operator algebra of CFT are identical when for P left, P right, change to P left and minus P left. So this is the same as exchanging momentum and winding. Because if you exchange momentum and winding, well, modulo the factor of 1/2, then P left doesn't change, but P right changes the sign because there's a minus sign. So this amounts to, this is the same as exchanging lattice with a dual lattice. Okay, so everything, so therefore you can think of even though we are defining string theory whose target space is RB divided by lambda, but if you define it as a conformality theory, then this is actually the equivalence of conformality. The space of conformality theory is actually smaller than the space of torus. The space of all torus is the same as classification space of the lambda. But the space of torus is the classification space of lambda modulo this identification. Okay, so I'd like to actually discuss this in more detail. So it's been useful to give you some example of this, so we can see what's going on. Okay, so let me try to work out the example where the torus is one-dimensional in a little bit more detail and see why something like that. Okay, so let's consider one-dimensional torus. This one. So namely, what actually we are considering is a map from two-dimensional worldsheet back to S1 times 124. So we started out with 26-dimensional Minkowski space and take one dimension out of it and periodically identify. So the simplest compactification. Okay, so let's choose the this lattice vector. So we define S1 to be equal to R divided by the translation by lattice. And let's define, well, let's put 2 pi in it, so we extract 2 pi. So let's define lambda to be integer multiple of 1, 1, where n is an integer. And if the torus is of radius r, then E11. So I'm writing E11 because it's one-dimensional. So E11 is r, right? So then it's clear that the dual lattice is generated by the dual vector. And the dual vector has a normalization 1 over. Okay. So then momentum is T left, which is equal to 1 over r, and with integer multiple, and then there's a there's a winding number, and P right is 1 over r of m minus r over 2 of m. So I said that the spectrum is invariant under this, so we can actually calculate the one loop partition function, torus one. The worldsheet torus partition function, which we discussed last time, is trace of q to the L0 minus 1 over 24 q bar L0 bar minus 1 over 24. Well, in general, we have 1 over the central charge over 24, so that is now this conformality theory, the central charge is 1, so 1 over 24, and q is e to the 2 pi I tau. Okay, so where at this tau is the periodicity of the torus, 1/2. Okay, so this is the calculation. And we just repeat what we did in the last lecture to calculate this Poisson function. And it's very straightforward. And it gives you this dedicated data function. So these are coming from this oscillator, absolute value square. And then there is a sum of momentum and winding. And since this is important, can you read the bottom part of the blackboard? So I know you are the front, so you can read it, but for those of you in the back, so this is Q to the 1/2 of N over R plus 1/2 of MR, where N and M are integers, and then Q bar is 1 over R and minus 1/2 of M of R squared. So the important thing is that the part which depends on the radius of the circle is only this lattice summation. This oscillator part is independent of that. And then if you look at this part, then actually this is invariant on the exchange of R to 2 over R. Right. So let me transcribe that over here. So Z is equal to the oscillator part. And this is independent of R times the sum of momentum and winding and this is invariant. And R goes to 2 over. Okay. And it turned out to be also it turned out that if you calculate operator product algebra of the theory, it's also invariant under this. So this is a very interesting thing. So it says a variety of things. One of which is the question of what is a moduli. What is the moduli space of S1? So in mathematics, moduli space is a space of geometric objects. And so in the case of a circle, there is of course a very simple answer in mathematics. What is the moduli space of a circle? In the classical mathematics, the answer is it's a half line starting from there, because for any positive real number, there is a circle, and different real number for different real number, they have inequivalent circle because the circumferences are different. So here I'm considering space of S1 as a Riemannian manifold. But the Riemannian manifold, the different radii correspond to different circles. So in math, in classical math, we can say that the space of this S1 is half line. But stringy math, would answer differently, because we can divide this half line at square root of 2. And if you think of the radius r here, which is greater than square root of 2, then if you consider 2 over r, it becomes less than square root of 2. And string theory cannot distinguish these two. So that means that for the moduli space of string theory on S1, we should identify these as the same point. So we should really think of the moduli space of string theory on torus, not as a half line starting at origin, but we should regard that as starting at the one square root of. So this is 2 over r. We should identify this. Okay, so so this is interesting. So there is some kind of identification going on. So the moduli, the size of the moduli space got reduced. You may think that, well, this is a bit funny because this is the infinite dimensional. This direction is infinite. This direction is finite. So what's going on? Well, in fact, in some sense, this part and this part are the same because there's actually a natural metric in the moduli space. You can define metric on the moduli space. The metric on the moduli space, in this case, is actually dr squared divided by r squared. So therefore, the volume of this part is infinite, but volume of this part is infinite too. Because if you integrate, if you try to measure the volume using this metric, in this case, length. But if you measure the length, in this case, it's logarithmically divergent at the origin. So in fact, both of them have infinite volume, and so it's a natural identification. Okay, but this is still mysterious. Why string theory should do that? What's the origin of this duality? So in order to understand this a little bit more detail, we should probably understand what's going on at this special point. Where is the special point? The special point is when the radius is square root of 2, where the lattice is duality itself. So we can let's try to sort of look into that in more detail and see what's going on. So we saw that, so let me transfer that over here. So in the stringy mass, we have this. Moduli space looks like that, where there is a square root. The radius is square root of 2. And then we have this identification of R to 2 over R. Okay, and so the question is that what is happening? What happens here? Okay, so let's try to analyze. Okay, so I have this formula here, and but let's calculate this partial function when R is equal to square root of 2. Okay, so this is equal to Q1 over 24. Is, and then you consider this summation. But it turns out that when R is square root of 2, this summation actually becomes nice because so let's try to write it out to see what's going on. So you have Q to the 1/2, but R is square root of 2. So that means that you have square root of 2 over n plus 2 square root of 2 of m square, and then q bar of n minus square root of 2 minus square root of 2 m over 2 square. So this is equal, therefore, q of quarter of n plus m square, and q bar of quarter of n minus m square. Right? So this is the but then what you see is that it's natural to try to sum them instead by considering this to be n and this to be n, because these are integers. But there are restrictions, and it's a very straightforward thing for you to figure out that you can actually write these things. It's a simple math, so I will leave it to you to figure this out. You can actually do this in this way. You can actually write this as sum over 2 things. This summation factorizes into 2 components. So you can write this as absolute sum of absolute value square of the 2 terms. Okay. So this is interesting because this first one is 1 plus 3q plus etc. square, and the second one is 2q to the quarter plus etc. square. Okay. So let's look at this. So what this means is that you start with 1, and then you have a 3 state with q, and you have 3 state with q bar, and you have 9 state with q bar plus etc. And then there is another thing coming from the other side, which is 4 times q quarter q bar quarter. This is less important for our discussion now, but we can write it in, right? So let's try to see what are these states. What are these 3 states 3? Okay, so these 3q. Well, so if you have, so this state is a vacuum. This state is a vacuum. This is a ground state. So this is the first excited. This is the first excited state, but this one of them we are familiar with. We can excite alpha minus 1 here to the vacuum on torus, and so this is one of them. But there are 2 other states with the same weight as this one, which is P ref is equal to plus or minus square root of 2. Okay, so these are the 3 states. And then this 3q bar corresponds to minus 1 bar of 0. And then P right plus minus is equal to prime minus of square root of 2. And then these 9 are combination of these. So you excite this and this. So the 9 state are like alpha minus 1 bar, alpha minus 1 P right is equal to plus minus square root of 2, alpha minus 1 bar, P left is equal to square root minus 2, and then P left is equal to square root minus 2, P right is equal to plus minus square root minus 2. Okay, so there are 4 plus 2 plus 2 plus 1 is equal to 9. So there are 9 states. Okay, so this explains these states, right? But okay, so far we looked at the torus part of string theory. But let me remind ourselves that the actual string theory is not just this torus, but there are other parts, which is that we have this worldsheet theory. Mapped into circle times R 24, D124, the 25-dimensional Minkowski space. And I said that for string excited in this direction, you have these many states for the low-lying state. But there are also excitations in this direction too. And so we should, so for full string theory, we should combine these two. So you can ask, well, what kind of massless state that this contains? Well, so for full string theory, we can consider states like that. The excitation in S1 direction, and the excitation in this direction, and the excitation in this direction, and the excitation in this direction. Where mu goes from 0, 1 to 24. So this is a vector, and this is a massless vector. These are massless vector. And these are Karuta-Klein compactification. Of the metric and the B field. Remember that in the 26-dimensional flat Minkowski space, the massless mode contains G mu nu and B mu nu and phi, right? And in fact, the phi is a scalar field, and if you dimensional reduce to one dimension, it's still massless scalar. And actually, that state corresponds to this. So this is actually Dirac. So this is not particularly interesting, but these are interesting. So if you probably heard about Karuta-Klein theory, that Karuta and Klein try to unify Einstein general relativity with Maxwell theory, and then what they considered was that instead of considering 4 space-time dimensional general relativity and Maxwell theory, they consider 5-dimensional theory, and compact by the extra dimension to a circle. And so suppose you consider general relativity in 5 dimensions where one of the circles is compact by, then the metric, they discover the metric tensor give rise to a vector field in 4 dimensions. What they considered was that, well, suppose you have G mu nu, with mu and nu goes from 0 to, in this case, 20, not 25. But then if the 25th direction becomes circle, then you can have a G mu nu, where mu and nu now goes from 0 to 24, or G mu 25, where mu only go from 0 to mu goes to 24, or you can have G25, 25, right? You have these things. Okay, and this one is a vector in 24 in the remaining 25 dimensions. So these are vectors. And so Karuta-Klein compactification naturally gives rise to massless vector. So these are massless vectors. These are massless vectors. There are 2 because you have G mu nu and B mu nu. So you have 2 massless vectors, and this gives rise. This G25 is this one. So maybe I shouldn't have said Dirac going G25, 25. B field does not give rise to this scalar field because the B field is unsymmetric. So we have this. But look like in addition to this massless vector field, which you would have gotten, if you have, oh, I shouldn't have erased this. Yeah, this one I can. Yeah, I can erase this one. In addition to, so this one, these two massless vector field coming from Karuta-Klein compactification come from these excitations. Right? So you have these two states, 3 states for the left moving excitation, 3 states for right moving excitation, gave rise to this massless vector. So this gave rise to 2 massless vectors in 25 dimensions. But look like, but what about these guys? These guys seems also, so it looks like they are also qualified to give massless vector field, and in fact they should, right? Because we can consider alpha minus 1 mu bar of P left is equal to plus or minus square root of 2. And alpha minus 1 mu P right is equal to plus minus square root of 2. And they are as good as those things. They are as good as those things. That has the same properties. They are dimension 1, 1. A conformal weight 1, 1, and these are highest weight state. And so there is nothing wrong with considering these states. So these give rise to massless vector. So therefore there are 2 more massless vectors. And then you also have 2 more massless vectors. There are more massless vectors. You have enhanced symmetry because these are gauge field. So originally you have Maxwell theory in this compact dimension, and there are 2 Maxwell theories. So you have U1 cross U1 gauge theory. You have 2 U1 gauge theory because you have G mu nu and B mu nu. Now this gauge symmetry is enhanced because you have 4 more gauge fields. So it turns out that this symmetry is enhanced to SU2 cos SU2. Okay. So so how do you see that symmetry is actually SU2 cross SU2? So let me finally explain how this works. But to see that, I'm going to use the state operator correspondence that we considered earlier. So the enhancement of symmetry U1 plus U1 into SU2 plus SU2 at R is equal to square root 2. So this is what I would like to explain. So remember that we have this space of this radius, which goes from 0 to infinity. But then there was a special point of square root of 2, where we have this identification R was 2 over R. So we wanted to understand what's going on in square root of 2. And we have seen some evidence that symmetry gets enhanced from U1 to square SU2. And so now I'd like to actually exhibit that the symmetry is actually SU2. Yes, how do you see that? So we use the state operator correspondence I mentioned earlier. Namely that remember that the idea was that for every state in conformal field, so you have a state, you can have a state and you can propagate this thing. You can map that by conformal transformation to concentric circle, time closing this direction. So this circle here is this circle. So there's a conformal transformation which does that. That can be used to map this state to an operator here. Okay. So so correspondingly, for each state in conformal field theory, there is an operator. So for example, if you have alpha minus 1 acting on the vacuum, the corresponding state is del of x. And then you have alpha minus 1 bar. The corresponding state is del bar of x. And if you have a state with momentum plus or minus square root of 2, the corresponding state is e to the plus minus I square root of 2 of x left. So I wrote x left because x left is equal to x plus I use this notation that x left is equal to minus I p left z plus summation n on 0, 1 over n alpha n I e to the minus nz. So reminding you the definition. Where this small x left and x right are conjugate to the left and right momentum. So so these are the correspondence. You can also write left and right here because there and there project onto left and right mode. So we can also write this in this way. Okay. So then how do you exhibit the symmetry? Well, first thing to note is that all these operators so these operators are transformed as vectors on the worldsheet because this has dimension 1 and they are holomorphic. Because this depends only on z, but not on z bar. So if I write them as j, so for the reason that will become clear, that I write j3 to be del of x left, and j plus minus to be e to the plus minus I square root of 2 x left. Then we see that the del bar of JA, where A is the 3 or prime minus, are all holomorphic. So in particular, it is conserved. So you have a conserved vector. And if you have a conserved vector, then there is a conserved charge. So namely that, so you can think of this as some kind of data type. These are conserved type. And then there is an associated charge. You can define by integrating z around J around some cycle. For example, if you have a torus, maybe a worldsheet is of this form, you can consider integrating this J around some appropriate cycle like that. And then this is conserved, namely that if I infinitesimally deform, if you move this cycle back and forth, the value of Q doesn't change because of the Cauchy theorem. Because if I have another gamma prime homologous to this gamma, then if I also integrate JA around this gamma prime and consider difference with this one, then this is equal to the integral of by Cauchy theorem. It's the same as the integral of del bar of JA in this domain, and by this property that it vanishes. So that means that this is conserved. Okay. So then you can ask what is the algebra of this conserved charge? And so you can easily see that the algebra of this conserved charge is makes SU2 here. Okay. So we can see how this works. Let's exhibit that. So if I calculate the operator product of J3 and JW in quantum field theory course, you might have learned the concept of operator product. So this goes like 1 over Z minus W square plus something finite. Okay, and then this is also the same as J plus Z J minus of W. It goes like 1 over Z minus W square. In this case, actually 2 plus finite. Okay, no, there is no finite. There is actually a term. So this gives rise to Z minus W of J3 plus finite. And then if I calculate J3 and J plus minus, it goes like Z minus W plus minus 1 of J plus minus W plus 5. And this actually, so the algebra, operator product algebra of this type is called Kac-Moody algebra. And in this case, it's a Kac-Moody algebra associated to SU2. In general, the Kac-Moody algebra is sort of one-dimensional generalization of the Lie algebra as a generator JA, JB. And then the structure of the algebra is of this form. Where a K is a number called level of Kac-Moody algebra, which are typically integers. And delta AB is a killing form. So Kac-Moody Lie algebra is typically associated to some Lie algebra. Of some Lie group G. So suppose you have a Lie group G, there is an associated Lie algebra. And then Kac-Moody algebra is denoted with hat on the Lie algebra. This delta AB is a killing form of this Lie algebra G, and FABC is a structure constant of this Lie algebra. Okay, so this is a special case of this Katsumori algebra where the algebra we are considering is SU2. Okay, and so in particular, this gives rise to conserved charge, which makes a standard SU2 D algebra. And so the operator product of these operators are controlled by SU2 symmetry. And from this, it follows that, that if you look at string theory in 26 dimension, compactified string theory on torus, one-dimensional torus, with the radius square root of 2, then in the remaining 25 dimension, the massless spectrum contains SU2 cross SU2 gauge field. And it's SU2 cross SU2 because there are 6 massless gauge fields, 3 for SU2 and 3 for the other SU2. And the interaction between them are dictated by operator product of the algebra of the corresponding operators. And these are controlled by SU2. And that's why you get no abelian gauge theory in compactified space with SU2 cross SU2 symmetry. So you have this enhanced gauge symmetry at this point. Okay. So you have this enhanced symmetry at this point, and so that means that if you go away from this special point where R is square root of 2, this symmetry is spontaneously broken. This symmetry is spontaneously broken, and so some of the gauge field becomes massive. So you have a Higgs mechanism. So the going away from this point where R is square root of 2 is a Higgs mechanism. If we have a Higgs mechanism, we can ask what is a Higgs field? Higgs field is a radius. So by having radius to acquire expectation value away from R, then you have a Higgs mechanism where SU2 is spontaneously broken to U1. Well, so if you have Higgs mechanism, you have variety of things going on. For example, that this very often, if you have Higgs mechanism, there are some discrete identification of the moduli space of remaining symmetry. And that actually R goes to 2 over square root of R duality symmetry is a remnant of that. So you can, so I'm running out of time, so I'm going to stop here. But the next lecture, I will start explaining why Higgs mechanism explains this duality symmetry. This is a very typical situation that when symmetry gets enhanced some particular point, there are some discrete identification of the moduli space away from the point, and that often explains the duality symmetry in string theory and gauge theory. So this is actually a very simplest example of this type. Okay, so we'll start that discussion next time. And then there are other special points in the moduli space. The R is 2 is another important point. So we'll discuss that, and then I think we're going to go to heterotic string after. Okay, so that's it for today. Thank you.